Hello everyone, welcome to this quick revision video of scattering. In this lecture, we are going to talk about scattering from exams perspective, your CSIR NET JRF exam, which will be held in barely a month, 26, 27 of December maybe. So in this lecture, we are going to only focus scattering from only exams point of view. This will be a very quick revision video, and we are not going to waste much of the time here. So let us start this video. So first of all, we are going to start this video by defining what is scattering. In layman's term, you have particle here and you have target particles here, and when this incident particles strikes this, it deflects from its original path from by an angle theta. This is called scattering. So what we have here? We have here is n, which is number of particles per unit area per unit time. Okay, these are incident particles. Incident particles, and small n is number of scattered particles per unit not area here. Here is we are talking in solid angle terms. Solid angle. Okay. Another term we define is differential scattering cross section. So what is differential scattering cross section? Basically is the ratio of small n by capital N. And then we have to define another term, total scattering cross section. What is total scattering cross section? Basically this differential scattering cross section sum over all the solid angle. And if we expand this, sin theta d phi. For most part, this value will be 4 pi if differential scattering cross section doesn't depend on theta. So we have defined here two terms. Okay. Another term we need to know is k wave vector. Wave vector value of this term is root 2 me upon h cut square. Okay. Another term we need to know is momentum transfer, which is k minus k naught. K is the scattered wave vector, and k is the scattered one, and k naught is the incident one. And if we solve this, we get value of q to be 2k sine theta by 2. This term you have to remember. Okay. Another thing you have to remember is, second, let me create some more space here. Another term you have to know is, for partial wave analysis, mostly problems are asked for S wave. S wave, for S, angular momentum is 0. Okay, so in this types of problems, f of theta, not f of theta, problems are mostly asked from total scattering cross section. So value of total scattering cross section will be 4 pi upon k square sum over 2l plus 1 sine square del L. This is the formula you need to remember. Okay, what is del L here? This is called phase shift. Another thing you need to know, for Born approximation, f of for Born approximation, this f of theta will be m divided by 2 pi h cut square sum over e raised to power I q r, some potential here, and then dq bar. This is valid for only central potentials, and in our exam we are mostly asked about central potential. Okay, and Let us also define what is central potential here. Central potential. Central potential. What is central potential? Central potential is some potential which have form of r raised to power n and then e raised to power minus mu r. These types of potentials are called central potential. And we have also some tricks here. We can solve f of theta. We can also solve from this equation, but it will take a lot of time. I won't recommend that. Instead, we have short trick. C naught is some coefficient, q is square momentum transfer, and then mu square. Mu is basically mass. This is reduced mass, and then q square raised to power n plus 2. And this formula is valid if n equals to 0 or minus 1. Okay, here we can n can take values like minus 1, 0, 1, 2. So this formula is valid for only these two. And if we have bigger values of n, then f of theta will be coefficient q square mu square, the same term, but additionally we have some other coefficient plus q raised to power n plus 1, u raised to power n minus 1 plus, then in the reverse order, same thing, q raised to power n minus 1, u raised to power n plus 1. And that's pretty much about it. This is all you need to know, and your problems will be solved from these topics only. What is the okay? Another relation you need to know is another relation which will be helpful for you is differential scattering cross section is equals to this is scattering amplitudes square. And if we expand this, if this scattering amplitude is a complex number, then this f of theta psi star. Okay, so these are all the concepts that you need to know, and from this concept only we can solve almost all the problems. I can't say that you can solve every problem, but out of 10 questions you can solve 8 questions at least. So generally there is 1 to 2 questions in this exam, and most likely you are going to encounter problems which which could be solved from these concepts only. Okay, so let us start solving questions. Just let me put more space here. Let us see what. Let us look into this problem. The problem says a free particle described by. Where is my name? Where is my name? Where is my name? Okay, I'm using white ink. Okay, so problem says a free particle described by plane wave and moving in the positive z direction undergoes scattering by potential. So we have potential here, and then we have to change value from V naught to 2V naught, keeping R fixed. Then the differential scattering cross section in this Born approximation. So for Born approximation, we already know this formula. For Born approximation, we know this formula, and this f of theta depends on V of R. If this all things are same, okay. So we can basically say that for our discussion, we can say that this f of theta depends on V of R. And then if this f of theta, if this V of R changes, then f of theta also changes. If you put 2V naught here, V naught, then these things changes. Okay. So what will be this f of theta? Then f of theta dash equals to V naught divided by 2V naught. Simply, we can say that this new f of theta is 2 times of f of theta. This is the relation we get from solving this. Let me put more space here. Okay, so now we have solved this, but we are interested in differential scattering cross section. So what is differential scattering cross section? F of theta square. Okay, and we have to also find differential scattering cross section for this new potential. So f of theta dash square, which is 2f, 2 times of f of theta square, which means 4 times of f of theta. Okay, f of theta square. So if we divide this from this is 1, this is second one. So if we divide for sigma 1 by sigma 2, we get 1 by 4, or we can say that second differential scattering cross section is 4 times of original scattering cross section if we double potential by 2 times. Okay, so let us see options. So in option 1, increases to 4 times the original value is correct. Okay, this problems was of very easy nature. If you know the relations, you can solve it. It didn't require any lengthy or any complex concepts. Okay, so now let us look into another problem. Another problem is the differential scattering cross section for scattered by target is given by this. If n is the flux of incoming particles, number of particles scattered per unit time is. Number of scattered particles per unit time is. So as we already know, what is number of scattered particles per unit time? So what we have to find here is small n. Small n is number of scattered particles per unit solid angle per unit time. How do we find that? By differential scattering cross section. By differential scattering cross section, n upon n. So value of n will be capital N times of differential scattering cross section of this particle. This is what we have to find. Okay, so for this we have differential scattering cross section, but this is per unit solid angle. And if we look into the problem says, if we look into problem says we have to find solution for particles per unit time, not per unit solid angle. So if we have to find without solid angle, we have to multiply solid angle here. So n without solid angle, without solid angle. Okay, so n times of d sigma upon this differential scattering cross section. It has to be integrated over all of the solid angle. Okay, so what is the value of differential scattering cross section? It is given in the problem. A square plus b square cos square theta. A square plus b square cos square theta. We have to integrate over solid angle. Solid angle is sin theta d theta d phi. Okay, d phi, it is not variable of d phi. We can take it out here. If we integrate d phi, limit for d phi is 0 to 2 pi. When we integrate here, then we get 2 pi. Now let us solve this. A square sin theta d theta plus b square cos square theta sin theta d theta. We need more space here. Okay, so here we have n 2 pi, we have a square sin square theta plus b square cos square sin theta d theta. Okay, here we can simply say that This sine theta will be converted into cos theta, a sine theta. Sine theta will be, integration of sine theta is cos theta, a square cos theta in minus, okay, limit for integration is 0 to pi. Value of pi is -1, value of 0 is 1, then -1 minus 1, and then minus a square cos theta, which will be equals to minus a square, which will be equals to a square, 2 times of a square. And if we solve this is b square, and we have to solve this cos square theta sine theta. Then let us take cos theta to be t, then sine theta d theta will be dt. So we can put here t square dt. And if we integrate here, this is t cubed by 3. Okay. And if we look at the limits for theta equals to 0, we have value of 1. Actually, let's go and take these values. We put here cos cube theta divided by 3. Theta for 0 it is 1, for 2, for pi it is -1. We have to integrate it from 0 to pi. For pi -1, for 0 it is 1, and if we integrate these terms we get value 2. So what we get? 2b square upon 3. So what do we get? Net value 2a square plus 2b square by 3, and we had common 2 pi n. Let us take this 2 common also. Then a square plus b square by 3 times of 4 pi n. Let us match our answers. Okay. So here we have 4 pi n, 4 pi n. Okay. These two terms 4 pi n, but these terms cancel. This is not equal, this is not equal, this term is. Okay. So we have solved this. What did we do? We only integrated, we only integrated differential scattering cross section, and then we had to find number of particles. Then we integrated and multiplied this term by n from n. Okay, let us look into another problem. Okay, so problem says particle of energy E scatters of a repulsive. This is the case of repulsive potential, repulsive spherical potential. In the coursework, you must have studied this. So in this case, we have potential here, and after solving this, we get value this. So question asks, what is the ratio of sigma total scattering cross section to the classical scattering cross section of a sphere? For these questions, if you don't already know, I don't expect you to solve this, but you will already know, you must know the results. Okay, so what is the cross section in classical case? It is 4a square. This is the classical case. For this case, we have sigma equals to 4 pi a square tan ka minus 1 divided by ka square. For b tends to infinity, b naught tends to infinity, we can take value of this to be limit tends to 0. Okay, so what do we get here? We get effectively value of -1 square. Then what do we get this? This is classical case, this is quantum case. What do we get value? 4 pi a square. So what is the ratio here? Ratio of q divided by q to the classical limit is 4 pi a square divided by pi a square, value is 4. Okay, let us look into another problem. So these types of problems are more frequent now, and these kind of problems are really easy to solve. Okay. So problem says we have central potential and we have to use Born approximation to solve this, and we have to find total scattering cross section. We have to find scattering cross section. Okay. So first of all, let us start by finding scattering amplitude. What is scattering amplitude? What is the value of n here? N equals to 1. For n equals to 1 case, we use bigger values. Okay, so here we use C naught q raised to power 2, mu raised to power 2, and then n plus 2. What is the value of n here? N equals to 1. 1 plus 2. Then C1 mu raised to power n plus 1, 1 plus 1, and q raised to power 1 minus 1, plus C2 mu raised to power 1 minus 1, q raised to power 1 plus 1. Then what do we get? C naught divided by q square mu square, and then power 3, and then C1, and this terms cancels to 0, mu square plus C2 mu raised to power mu cancels, and then q square. What do we need here? We need, okay, so what do we need here? We need total scattering cross section. No, differential scattering cross section. We need relations between differential scattering cross section. It will be value f of theta square. And we are only interested in this q's value. See, we are only interested in this q's value, and problem is asking about dependence. Dependence means proportionality. So we are going to ignore every other term here. Okay, so here we have q square raised to power 3, and then C2, we are going to ignore this also. Here we have q square, and then whole square. Let us solve. 3, 3, 6, q raised to power minus 6 plus 2, which is raised to power 2. So q raised to power minus 4 power 2 is q raised to power minus 8. So as you can see, this is really easy to solve. This tricks works for any central force problem, central potential problem, for Born approximation, and after putting values, we can simply get, where is my pointer? Okay, so this value is correct. These problems need bit of solving, and you have to spend time here. Okay, so problem says we have some potential here, and we have cube here, we have cube like this, and then we have potential, and what we have to find is total scattering cross section. Total scattering cross section. For scattering amplitude, we already know the relation. What is the relation here is m divided by 2 pi h cut square minus q r v of r sum over all space. This is r. Okay. So here we are talking about low energy scattering, and low energy scattering we are here. Yeah. Okay. There is no mention of wave vector or momentum transfer. So we will take value of this to be equal, which implies that this term will be 0. This term will be 1. So we are only interested in this problem. Okay. And then as we can see that this has form of discrete values. So for discrete values, we can say that this is potential V naught and then V naught A cube and cube R minus R naught. You should have some understanding of direct delta potential. Direct delta potential is R minus R naught is 1 if R equals to R naught and 0 otherwise. Okay. For cube, this Ri equals to A. Okay. And this R, if this R equals to A, because we are taking cube of side A, then this term will be 0. This will be the case for every single corner. For the cube, we have 8 corners. Okay. So this term will be 1 for 8 times. So V naught A cube, and we have to sum every term. So 1, 2, 3, 8 times. Okay. So what do we get? Scattering amplitude to be minus m 2 pi h cut square and then 8 times of V naught A cube. Then we have to find total scattering cross section. For total scattering cross section, we need differential scattering cross section. Okay. What is differential scattering cross section? Simply square of this term. M square 4 pi square h cut power 4 64 V naught A cube. Okay. And then we have to take value of this term to be 1 second. We have to take value of this term to be okay. I have squared here. Okay. Then now we have to take value of this term will be total. So we have to take values of solid angle, and if we take values of solid angle, this term is multiplied by another terms also. Then we take values of this and then multiply it by 4 pi. Okay. Not here. Is multiplied by solid angle. Value of this is 4 pi, and this is total scattering cross section. Okay. So total scattering cross section will be 4 pi times of 64 V naught A cube m square divided by 4 pi square h cut raised to power 4. Pi we get only 1 pi. So value here is 64 V naught A cube m square divided by pi h cut power 4. Let us see if our answer matches this. 64, 64, 64, yes, 64 A square upon pi. Then, yes, we have two answers which are matching. This term is right, this term is pi square, not pi square. And we have h raised to power 4. Here we have only 2. So this answer will be correct. So the thing here is, I don't expect you to solve this question. If you have decent conceptual clarity, you can solve this. But as you have already seen, most of the questions are not like this. Most of the questions can be solved from simple tricks. Okay. So let us see another problem which we can solve from very. So we have another problem here from partial wave. Change the plan. Partial wave analysis. Here it says phase shift of 30 degree is observed when the beam of particle of energy. So for one phase shift, we have energy 0.1 MeV, and then for another phase shift we have to find energy. And the question says that cross section does not change. What do you know about partial wave? That cross section is 4 pi k square summation over 2l plus 1 sine square del l. For S wave, l equals to 0. Okay, so total scattering cross section is 4 pi by k square and then sine square del l. Or we can say that total scattering cross section 4 pi sine del l upon k square k whole square. This is total scattering. For first particles, 4 pi times of sine 30 degree and then value of k root over 2me upon h cut square. And value of e here is 0.1 MeV. And then for second, 4 pi sine 60 degree root over 2me upon h cut square. We have to find value of this e and then square. So every term cancels out. From squares, square cancels. So we can say that sine 30, value of sine 30 here is 1 by 2 divided by root over, all terms cancels, root over 0.1. Okay, here value is root 3 by 2 divided by root over e1. 2. This 2 cancels also. So what do we get effectively? Effectively we get e1 equals to 3 times of 0.1. All things are in root. If we take root outside, we get value of 0.3 MeV. And that is what we needed to find. Answer. Okay. So what is the answer here? Answer is 0.3 MeV. This is the last problem. And let us do this. Differential scattering cross section for central potential is given here. Born approximation, again same pattern. Born approximation. For approximation, central potential value is given here. Central potential beta r raised to power minus 1 e mu r. For n equals to minus 1, we know f of theta is proportional to q square mu square, and then n, value of n is minus 1 plus 2. So effectively q naught divided by q naught square plus mu square. That's it. But this doesn't say. We have to find proportionality between dependence on scattering angle is. Differential scattering cross section is given. This is calculated for first Born approximation, and then we have to find scattering amplitude. Differential scattering. So we have to square f of theta. Okay, simple. We have to square f of theta here. Implies c square q square mu square whole square, and then we know q is 2 sine theta by 2. So we can say that c naught square 2 to the 4 sine square theta by 2 plus mu square, something like that, power 2. So if we are already interested in this term is differential scattering cross section, so we are only interested in proportionality. So we say that this term is proportional to 4 sine square theta by 2. Let us remove this also, plus something raised to power 1 by 2. Let us see which option matches. Sine square theta by 2, a square, everything is same. So power minus 2. So for minus 2, this term matches. Okay. So we have concluded scattering, and you should not waste much time on scattering. This is whatever I have taught you is enough for exams perspective, and 70 to 80% of the time you will be able to solve question from this thing only. And if you can't solve problem from this much amount of knowledge, probably those 30% of the topic will take you hours to study. So I won't recommend that. Please do this diligently, and if you like the video, please share it. Thank you.